Hello, we're going to talk about analyzing graphs of polynomial functions. One of the questions that comes up is how do you find zeros? And we should start this with the question of what is a zero? What is the definition of a zero? A zero is an x-intercept of a graph. So if I've got a curve that looks, say, something like that, there is a zero, there's a zero, there's a zero. All those x-intercepts are zeros. 0, 0, and 0. So that's what a zero is. When we ask you to find a zero, to find a zero means to give the x value of that zero. And the reason we only care about the x value is because of another reason, that it's called a zero. A zero is anything, again, that is an x-intercept, and all x-intercepts have a y value of 0. So then we call them zeros, and then we just give the x value for that 0, and it's understood that that is an x-intercept, and then we're giving the x value because the y value is understood to be 0. Okay? So let me give a practical example of this. Find the zeros of, let's say this function here, f of x equals 2, oops, that's a really bad 2x to the 4th minus x to the 3rd minus 5. So that's a polynomial function, and how do I know that? Because this part here is a polynomial, okay? And remember, polynomials are things with the variable having whole number exponents only, and where parts of it are separated by pluses or minuses. So one thing I might do in order to do this is I might graph it. And to graph it, I might create a table of values. A table of values, some people think of this as a number graph, a quote-unquote number graph. This is typically learned in Algebra 2. So we want to, the idea when you create these tables is that you pick x values and you plug them in here, and you generate y values. You get answers which are y values. So we got to pick some x values here. A real easy one is usually 0, because if I put in 0 there and there, I get 0 minus 0 minus 5, which is -5. So 0 is a real easy one to put in. Let's try -1. So that one will be a little more difficult, but we can figure it out. If I do f of -1, that means every time I have an x, I'm going to substitute a -1. So it'll look like this: 2 times -1 to the 4th. Minus can always be written as plus negative, and I'm going to do that. So plus negative of -1 to the 3rd plus -5. So that's going to be 2 times, and so I need to figure out -1 to the 4th, which is -1 times -1 times -1 times -1 4 times. Okay? And if you do that, you wind up with +1. You can check that for yourself, but you do wind up with +1. Then plus negative, and then I got to figure out -1 to the 3rd, which is -1 times -1 times -1. So the first two, -1 times -1, gives you +1, and then times another -1 gives you a -1 plus -5. And now we got to figure out answers to all of this. So 2 times 1, well, that's pretty simple. That's just 2. Negative times negative, and the reason I say negative times negative there is because what we're talking about is a negative symbol times a negative symbol, and typically anything that's right next to each other, you're always talking multiplication. So when I look at that, I'm always going to think multiplication. So negative times negative is positive, so I get +1 there, plus this -5, which is, if I put these two together, that'll be 3 plus -5, which is -2. So if I plug in -1, I get out -2. And the trick here, I'm going to erase all this because I need the room. The trick here is that you got to keep doing this, and for these polynomial functions, you actually have to come up with many of them. However, I do want to point out a trend already. Notice there that we go from -5 to -2 in the y values. They're both in the negative, but we're climbing, right? In other words, on the graph, we started at a y value. We started at 0, -5, which is there, and then when we went to -1, we came up to -2. So it looks like we're trending up with that. And you can see that in the numbers also. So let me pick another negative number. Okay, let's do -2, and let's figure out f of -2, which is 2 times -2 to the 4th, plus negative, remember I'm using plus negative instead of minus, times -2 to the 3rd, plus -5, is 2 times -2 to the 4th, that's -2 times -2 times -2 times -2. So think of it as two groups of -2. Think of it as -2 times -2 times -2 times -2. So if you put those two together, you get a +4. If you put those two together, you get a +4. So in total, you get 4 times 4, which is 16. So there's how I come up with that number. You could, of course, put it into a calculator, but come on, that's too easy to put into a calculator. Plus the negative of, And now we've got negative 2 to the third, which is negative 2 times 1 more negative 2. So that's 4 times negative 2, which is negative 8. Okay? Plus that negative 5. And we'll figure out that 2 times 16 is 32. Plus negative times negative again, which gives you positive, so positive 8. Plus negative 5. And then 32 plus 8 is easy to put together. That's 40. And then 40 plus negative 5 is like 40 minus 5, which is 35. So if I plug in negative 2, I get a positive 35. So let's look again at how this is working on the graph. Notice that here in the y's that we're generating, we went negative, negative to positive. And so we're trending up here. We go from negative 5, let me put negative 5 way down there so I can put positive 35 way up there. And as I'm sort of moving backwards here, I'm going up, okay? So that's what's happening now. Notice this tells me that already there's a 0 right there. Remember, zeros are x-intercepts. So somewhere in between, and you can see this on the table pretty well, somewhere in between these two, there's a 0. So that means that somewhere in between negative 1 and negative 2, there's a 0. Okay? Somewhere between the x values of negative 1 and negative 2. So I found 1, 0. Now, the next thing to know, the next thing to understand is how many zeros are you possibly looking for? Okay? And that is told by the degree of the polynomial. Now remember, the degree of the polynomial, which I circled that number, the degree of the polynomial is told to you by the highest exponent in that polynomial. So right there, again, the degree is 4. Now, why is that important? Because the degree of the polynomial also tells you the maximum number of zeros. It doesn't tell you, it doesn't tell you the total number of real zeros necessarily, but it tells you the maximum number. And the reason I say that is because sometimes you get imaginary zeros. So being a real 0 winds up being important, okay? So we found one of them. It's somewhere between negative 1 and negative 2, okay? Let's look for another one, and let's start taking positive numbers. Let's look at positive 1. So let's figure out f of 1. That's 2 times 1 to the 4th plus negative of 1 to the 4th plus negative 5. This isn't too hard to figure out. 1 to the 4th is 1 times 1 times 1 times 1. I think that was 4 of them. So it's 2 times 1, because 1 times anything is itself. So 1 times 1 is 1, times 1 is another 1, times 1 is another 1. Plus the negative of 1, oh, and I messed that up, didn't I? It's supposed to be 1 to the 3rd. Sorry about that. So it's the negative, that negative right there, of 1 to the 3rd, and 1 to the 3rd is 1 times 1 times 1, which is 1. This negative has nothing to do with this 1 to the 3rd, so it stays out there as I get this answer, okay? Plus negative 5, and then 2 times 1 is 2, plus negative 1 plus negative 5. A negative plus a negative is a bigger negative, a bigger looking negative, I should say. So you leave the negative out front, and then you add the numbers. 1 plus 5 is 6, and 2 plus negative 6. When you add a positive and negative number, you subtract them and go with the sign of the bigger one. So negative 6 is, the 6 is bigger than the 2, so the answer is going to be negative, and then 6 minus 2 is 4. So f of 1 is negative 4. So now we have to look at this number and that number, okay? And notice they're both negative, so there's no 0 hidden in there anywhere. So let's look at, let's say, f of 2, okay? So f of 2 is 2 times 2 to the 4th plus negative times 2 to the 3rd plus negative 5 is 2 times 2 to the 4th. That's 2 times 2 times 2 times 2. 2 times 2 is 4. 2 times 2 is 4 again. 4 times 4 is 16. They're all positive, so it all comes out positive, of course. Plus negative, again, that's that negative. 2 to the 3rd, which is 2 times 2 times 2, so that's 4 times 2, which is 8. So we get negative 8 there, plus negative 5. And then 2 times 16, that's 32, plus negative 5 plus negative 8 is a negative answer because you're adding two negatives, and add the numbers. 8 plus 5 is 13. And then 32 plus negative 13 means subtract them, take the sign of the bigger. The bigger one is positive in this case, so this will wind up positive. And 32 minus 13 is, let's see, I got to borrow 12 minus 3, that's 9, and 2 minus 1, that's 1. So we get a positive 19 there. So f of 2 is 19. In other words, when I plug in 2 for x, then you get 19 as your answer. Okay? So let me get rid of that. So we found two of them, and let's take a look at what we've got so far. And I'm going to put, let me take this up real high and put the 35 way up here. And let's say that's negative 5, let's say that's negative 1, something like that. I'm not being accurate here, I'm just trying to sketch things, okay? And then, so we're going to look at 0, negative 5, negative 1, negative 2, so maybe somewhere around, whoops, not around there, but around there, negative 2. And then if that's negative 2, we go all the way up, we jump up to 35. And then at 1, we're at negative 4, so somewhere like there. And at 2, we already jump up to 19. 19 is going to be sort of somewhere around halfway. Let's put it there. Again, I'm just sketching this to get an idea. And so it looks, starting to look something like this. And in fact, that is what it looks like. And the advice I would give, because this is fairly tedious, and this is something that isn't typically a short process. if you're trying to make these tables of values like this by hand, this can be pretty tedious. So I'm going to give you something that I think is pretty helpful with these types of problems, and that is Desmos.com. And Desmos.com is a really wonderful online or offline graphing calculator application. You can do it straight off of a browser, or on a phone or a tablet. You can download it. You can download the app straight to your phone or tablet, and it will work offline, which is a really nice feature, so then you don't have to worry about whether you really have Wi-Fi and things like that. So if you go to Desmos.com and use the graphing calculator, you could put in this equation right here. In fact, you could put it in exactly like this. You might have to play around with it to figure out how to do the exponents. I'll tell you, though, you want to use the caret button to create the exponents. And you just want to make it look exactly like that, and it will graph it for you. And you can zoom in and zoom out on that graph and change things about that graph to be able to look at it. Okay? Another thing you might ask, I'll go to a new page here. Another thing you might ask is, or say to me, especially if you're a student of mine, you might say, well, you've shown us with a lot of the functions that we can tell how it moves, how it shifts. Let me give you an example. If I gave you f of x equals, and I wrote this, x minus 2 squared plus 3, you can tell me, or you should be able to tell me exactly how that shifts from what we call the parent function, which is the simplest version, which is x squared. And the parent function looks kind of like that. And then this new function, this, actually I will keep that circled. This tells me there's a shift in the x direction of positive 2. This tells me there's a shift in the y direction of positive 3. X's move opposite what you expect, y's move as you expect them. Unfortunately, this method is not helpful when dealing with most polynomial functions. And the reason is because we don't get it in a format where we can really see that shifting in the equations. So you can't really tell what it's going to do without either graphing it with technology, Desmos or some other graphing technology, graphing calculator, whatever. What you can tell is something about what the degree tells you. And I want to go back to this page and again talk about the degree. So the degree for this one was 4, but notice I only have 2 zeros, right? There's only 2 zeros there. And the problem with that is, but the degree is 4. Shouldn't I be seeing 4 x-intercepts? Well, There are two possibilities, because we made a table for this one instead of graphing it with technology. We might not have graphed all of it. There is a possibility that both of those could turn down again. That happens to not be the case in this case, by the way, but it could have been. So the other explanation is maybe these two repeat, which is a possibility, and maybe there are two imaginary zeros, so that is complex zeros, and those don't show up on the graph. So, and that is indeed the case with this particular function. I have two real zeros, okay? So there are two real zeros on this. Again, they are right there and right there. And those two real zeros, one of them is between, and we're just going to talk about which consecutive integers it's between. It's between -2 and -1. So that's that one right there. And the second one is between, so by the second one I mean that one. The second one is between 1 and 2. Now, just because you see the numbers 1 and 2 twice doesn't mean this is going to happen every time. This is a coincidence. It means nothing. So don't get worried if it doesn't look like that in others, okay? So I'm trying to look at the questions that I had here, and the questions that are going to become important. Notice that down here, right there at the bottom, this is what we call a relative minimum. It's actually the minimum for this particular function, but it can be called a relative minimum also. And let me clear this one out and talk about that just a little bit. Let's say that we have a function, and I don't know what the equation for this function is, but let's say it looks like that, okay? Let's talk about what you can tell just by looking at this graph. First of all, it has 1, 2, 3, 4 x-intercepts. So there is at least 4 real zeros. Now again, you could have repeating real zeros, and you could even have imaginary zeros, that is complex zeros, and they wouldn't show up on this graph. But what you can say is that the smallest degree must be 4. Okay, so at the very least, we know that there's going to be f of x equals something with an x to the 4th, and there might be other stuff. But what we don't know, we know for sure there's at least an x to the 4th. this one can't start with an x to the third. It has to at least have an x to the fourth in it, but it could have an x to the, well, not, technically it can't have an x to the fifth, but it could have an x to the sixth, an x to the eighth, that sort of thing. And anyways, it could be bigger, but it cannot be smaller in the degree. Okay? So I've talked a lot about all of those things. I want to note the turning points. Here's a turning point, also a relative maximum. This is a relative minimum. There's another relative maximum, and those are turning points in the graph. And notice we have a maybe degree 4 polynomial. Let's assume that it is a degree 4 polynomial. And at the very most, the maximum number of turning points would be 3. And I can do that if I were to ask it the other way also. If I were to say, okay, what is the maximum number of turning points for a polynomial of degree 4. So what you could do to figure out the answer to that is you could say, okay, let's assume that this tells me that there are 4 x-intercepts. That may not be the case, but it could be. And let me draw something that gives me 4 x-intercepts. 1, 2, 3, 4. 1, 2, 3, 4. Degree 4 could have 4 real zeros, meaning 4 x-intercepts. Then you can count the turning points. 1, 2, 3. So max of 3. And that's how you would talk about that. So I think I've talked about everything I need to with analyzing graphs of polynomial functions. I encourage you to use the technology Desmos.com to help you when it comes to problems like this, because it can be very, very helpful. Again, that's Desmos.com. Okay, thank you very much.